Okay, I think we'll get started. So if you're coming from the G and Lewis project, I encourage you to look at the introductory video to make sure this is the right sequence for you. Otherwise, the topic of today is circular motion, and in particular, uniform circular motion. So we've been talking about motion in two dimensions now. We had our one-dimensional case. We have uniform motion where the velocity is constant. We have constant acceleration. With that, we were able to focus address the ramp problems by just a rotation of coordinates, so that we've reduced that to a one-dimensional problem by eliminating the y or y prime variable as we were using. Then we talked about projectile motion, and because gravity is always pointing along the y direction and the x and y directions are orthogonal, we saw that projectile motion broke into both a uniform motion in the x direction and then constant acceleration motion in the y direction. Well, now we're going to talk about circular motion, and this too is certainly two-dimensional. Because we're rotating around in a plane. So imagine this model airplane that's attached to, has a motor and it's attached to a wire, and it can fly at a constant speed. But because it's on the wire, it will go around in a circle, round and round in a circle, and that will form a plane, and it will be moving in that two-dimensional plane. So drawing it on the board here, this will have a x and a y position all the time. Now, if we think about this motion, it's special because the speed is constant, but that does not mean the velocity is constant. The velocity is changing all the time because it's changing its direction. Remember, velocity is a vector, so it's speed with a direction. Speed is constant here, but the direction is changing. So we're representing that here with these vectors. So as this plane moves, if it's down here, the vector points down here. So this would be at this point, and then here the velocity vector, down here the velocity vector is going this way, round and round in this circle. We call that uniform circular motion. Uniform because the speed is constant, or this magnitude of the velocity is constant. This probably should be a vector here. Right? So this is equal to v, which is equal to speed. This is always tangent to the circular path. So whatever point we're on here, the vector runs tangent to that path. Now, let's kind of break this down. Let's take two very close points here. These 2 points here. We've moved just a little bit along this circle, and our vector, the length has not changed, but the direction has changed just a little bit. So how do we compare vectors? Well, we're going to want to look at the change in velocity, so final minus initial, or v2 minus v1. So we're going to pick these guys up, put them at a common point, right? And our delta v is then going to be this vector. And they differ by an angle theta. They differ by an angle theta. Let's look at so that's the velocity, differ by this angle theta. These are going to be coming from a couple of points here. So maybe it's these 2 points, right? Very close. There's a distance r. These are both r because it's on a constant, in this case, the constant wire is the same length, the radius is the same length, and it traverses this exact same angle, theta. So we have r, and d. This is the displacement. And if we make that small enough, yes, it is displacing on an arc, but if we make that small enough, we can treat it as if it were linear and create a little triangle here. And so if we compare these two triangles, we have similar triangles. So they have the same angle, the two sides are equal, right? Not to each other, but we have two equal sides, r and r. And here, what are the length of this? The length of these sides, the length of the sides are just the magnitude of the vector or the speed, right? And then this is the magnitude of the change in the vector. So we have similar triangles, and then going back to 10th grade geometry, similar triangles, we can write this ratio. So the ratio of D to R is the same as the ratio of the magnitude of the difference to the magnitude itself. So the magnitude difference over speed. That's just the geometric property of these similar triangles. Now, D, this is the displacement. Well, that's going to be given by the velocity times time, right? This is what we've been talking about. So this would be considered sort of uniform motion. This is well, I shouldn't say that, but it's just going to be given by this speed, the magnitude of the velocity times time. Moving along, the direction would depend on where we are here. So if we're looking down here, then the direction will change, but that same distance covered, the displacement, is going to be the same. So this is not a vector, this is just the distance. And then let's take this ratio, right? And we'll take this equation. So we'll say this is equal to D over R. Well, what's D? D is right here, right? Over R. Now let's bring up this to this side, right? We'll multiply through by both. And so we have this change in velocity is equal to the magnitude of the velocity, or the speed, squared dt over r. Okay? So this is equal to the speed. Sorry to jump in here. I didn't write down what I said. So this is the speed, right? So this is not true, but this is the speed v right here. So make that change in your note moving forward. The rest of what is going on is correct. Okay, well, let's look at the acceleration. Acceleration, as is just using our normal formula, the acceleration vector is the change in the velocity with time, right? Delta v, so that's a vector. Let's look at it as, this should have a arrow. Let's look at it as a magnitude now. So just the magnitude of the acceleration. And we get this. Okay. All right, well, let's do some substitution. We have this equation up here. So that gets substituted into here. Okay. And we see that this brings in a delta t in the numerator and a delta t's from the denominator, so those cancel. So actually the time dependence drops out, and we get a magnitude equal to the speed squared over r. So now we want to get this back to a vector, right? This is the magnitude. So we have to give the magnitude and the direction. Well, let's go back to our picture now. So in order to change the velocity such that we go in this circle, if I'm going this way, then I have to pull exactly perpendicular to it. So I'm going in a tangent vector here. So my acceleration has to be a normal vector, but pointed inward. Right? So perpendicular to the surface, or to the curve at this point, and always directed inward. So in these circular motion problems, it's awkward to use a vector in the sense of like two coordinates or drawing an arrow, because we're drawing kind of the same arrow, but pointing always pointed to the center. So usually what we say is the speed squared over r directed inward, and that's a magnitude and direction. So that's our acceleration. Now let's look at this in practice. How is this used? Certainly in something like this, and that feels like a little bit restricted because we're always talking about just this plane stuck to this wire. Well, let's imagine here now a car running across a highway, and then it goes into a dip. What we can do is we can model that dip as part of a circle. So there's this dip here. Then we just we draw a circle that would trace the dip, and then we complete the circle. And so as the car's moving along this part of the circle here, right, it's just like the plane, only on part of its curve. And likewise, if we have a little bump, if there's a little curvature bump, we can just superimpose here a circle, and the car, usually we're worried about what's happening in the car when it's going over that bump, and so it's traversing that circular path. So let's take an example here. Let's say the car's moving at a speed of 30 meters per second, and the radius of this circle is 200 meters. What's the acceleration? Well, it's going to be 30 squared, right, over 200, and that works out to be 4.5 meters per second squared. It's an acceleration, so it's meters per second squared, right? And so we say, okay, that's acceleration. When it's down like this, that's acceleration directed upward. That's what the road is having to do to push the car back along this curve. And then right here, the acceleration is downward. Okay? So it's always directed inward to the circle. So it's important that we superimpose that circle on there so that we can get the correct direction to the acceleration. If we're somewhere over here, right, if we're coming on this side of the curve, then we're directed this way. So our acceleration vector is always changing as we go over that hill. Okay, well, this is related to something that you often hear about, like G-forces or G's. These are not forces, actually. We haven't talked about forces yet. They're absolutely related to forces, and so that's where the name G-force comes in. But right now we're just talking about acceleration, and we have the acceleration due to gravity of the Earth. And so one way people measure that is what percent or how many times the acceleration of Earth are we experiencing. So you hear about fighter pilots or the Blue Angels or something where they make these strong curvatures in their flight patterns, and the pilots experience high G forces or high G's. Well, how we do that is we just say, we just represent the acceleration or the magnitude of the acceleration as just some number times G, or how many times G is it. So let's use our example of the car. What is the G force we experience, or the G's, when we go down in this dip, for example? Well, we calculated that the acceleration was 4.5 meters per second squared. G is 9.8 meters per second squared. So if we take this ratio, we get 0.46, right? So if we multiply 0.46 times 9.8, we get our 4.5 meters per second squared. So our acceleration is this, and so we would say we experience half a G, basically, 0.46 G, or we experience a G force of 0.5. If we were taking a really sharp turn and going really fast, then we might experience something greater than the gravitational force, which we would say maybe we experience like 3 Gs or so. Right? And eventually we have limits to our physiological limits of how many Gs we can experience without just passing out because our blood can't flow the way it's supposed to and get to the brain. Okay. All right, so that's uniform motion. We have a little bit more to talk about because, yes, this is 2 dimensions, and we certainly addressed that here with these vectors, but it also feels a little bit constrained, right? Remember when you had the ramp, it definitely was 2 dimensions, but it was constrained so that we were able to reduce it to 1 dimension. Well, the same thing can happen here, a little trickier though. We can represent this as a position along this circle, right? And then we can represent the position as an angle around the circle. So we'll get to that. We'll get to that soon. But we can really reduce this problem actually to a 1-dimensional problem. But when we do that, we're talking about traversing an angle rather than a distance. So that will be coming up. But if you were thinking, well, there feels something constrained about this problem, is that helping us? And indeed it is. We can treat this as a 1D angular problem, and we will do that. Okay, the last topic of today is kind of a separate thing. We're still talking about motion, but I want to talk about relative motion and the concept of an observer. So let's say we've got this train bed, and we're given the phrase, or we're told the train is moving at 5 meters per second, plus 5 meters per second, and person A on this train bed is running at 3 meters per second. That's actually an ambiguous statement, but we probably would all be thinking the same thing. And so in loose everyday speak, it probably all would make sense to us, but technically, that's an ill-posed problem. We can't really say, what does this mean? And let's see why that is. And the way we have to think about this is who is doing the observing, and then we need to keep careful track of that. And in fact, the way we're probably all thinking about this is that if I'm standing on the surface of, off of the train, and I'm watching the train go by, then the train is moving at 5 meters per second, right? So we would say person B standing on that train is moving at 5 meters per second. But then when we hear this phrase, the person is running at 3 meters per second, we subconsciously shift and we think about, oh, I bet that means that if we took this person and put them on a track, they would be running at 3 meters per second. And so if we were to look down onto the train bed and see how fast they're going, or how many meters per second are they traversing, it would be 3 meters per second. Right? And that's what we would probably think about, and that's probably what would be meant by this problem. But notice we have shifted observer here. This person now would observe this person moving at 3 meters per second. But our original observer, person C, would actually be seeing this person moving at 3 meters per second on a train that is moving at 5 meters per second. So they would be perceiving the person moving at 8 meters per second. Okay? And I think when you just hear this, your brain just takes over and kind of puts in the most obvious thing that's meant. When you stop and make yourself think about it, it is generally, I think, pretty intuitive, but how to systematically think about it, I think, is where various of us gets hung up. For some of us, this will come just like that, because your intuition and your systematic way will connect. And for other of us, we'll have to work a little bit harder so that we can get those two connected. So let's think about observer B and observer C separately. So for observer B, we're going to say they're in the primed system. So whatever we report, we're going to put a prime on it. So when we're talking about velocities or speeds, we'll put a prime on it. So we would say from person B's perspective, person A is moving at 3 meters per second. The train is moving at 0 meters per second because we're standing on the train, and if we look straight down, it is looking like the train is not moving. Right? So if we couldn't see anything but the train, it would feel like we're standing still. And so the train is moving at 0 meters per second. So what does it mean for then person C? Well, the person C is receding into the background. So one thing I like to think about, or that I think could be helpful, is if we're thinking about person B, imagine putting a GoPro camera on that person. And so that camera is stuck to that person's head. So whatever that person is doing, the camera is doing. And then think about what you would see if they uploaded their video to YouTube and you were watching that sitting on your couch. If we were sitting here, right, you would see this person coming at you at 3 meters per second. They would be coming towards you, right? If we now direct the camera to person C, they would be heading off away from you at minus 5 meters per second, right? They'd be heading in this direction, in the negative direction. Okay, well now let's look at from observer C perspective. So take that GoPro camera and put it on a person C's perspective. If they look at the train is going to be moving at 5 meters per second. So when they look at person B's velocity, who's just standing still on the train, they would expect, or we would see, if we watched the video, we would see the person moving in the positive direction at plus 5 meters per second. But now when they observe this person running, they will observe the train moving at 5 meters per second, and then the person running along the train as moving an additional 3 meters per second. And so from the perspective of that GoPro camera, person A would be running away into the positive distance at a speed of plus 8 meters per second. Okay? So this idea of who is observing is a really critical one in physics, and we will wait all the way till the end of the year, not even the end of the semester, to come back and really explore this further. It has some really important ramifications when we think about things very carefully. For us now, it's all going to be pretty much common sense, but we will have a few problems on this where you want to sit down and you want to really write out what each person is seeing, and try to avoid letting your brain just slide around without you not knowing what it's doing. It's probably doing the right thing, but if you don't really pin it down and ask yourselves, why is this the case, then you don't really truly understand it. And then when we get to situations where it is going to be strange, like at the end of the year, then we have nothing to build upon. So think about motion from the perspective of someone observing it. And this idea of a GoPro camera can be really helpful in that, I think. All right, so that's it for today. We will be, again, working on some of these in the homework, and then we'll, as I mentioned, talking about angular motion as well.